Alright, I wanted to continue with a review of some circular motion and show you how this applies to Newton's laws. And what I've chosen here is I went to 1987. That was like my second year teaching here at Turner. No, I'm not old. I know I only look like I'm 30. But what I did is I found a problem here, and basically you can't really see it from this picture. But it's got a guy pulling a kid back in a swing, and all they tell you is the child in the swing has a weight W. So they give you that much. They tell you the length of the swing is L, and they say he pulls it back at an angle of theta to the vertical. And so if you want, you can probably Google search this and just type in 1987 Physics C Mechanics number 1, and it'll pop this problem up. You'll probably be able to find this. I'm sure this is out there. The solutions maybe not be, but this, you might be able to find it from the College Board. Well, maybe not. That's a little early. All right, so the first question says, the guy's just pulling the rope back, and it says find the tension in the rope. But they want the answer in terms of W and theta, and they want you to figure out the tension in the rope. So what I want to do is I want to look at this and I got to say, okay, I got to choose a place. If I want to find the tension in the rope, then how am I going to do that? Well, to do that, what I'm going to do is I'm going to look at this kid right there in the swing, and that's going to be my system. So I'm going to draw a free body diagram of that kid on the swing. So here's the kid on the swing, and I'm going to represent him by a center of mass. By a dot that represents a kid's center of mass. Now, the next question, you can't read it here, but it says, find the horizontal force exerted by the adult. So, really, if you think about it, you've got this kid right here. You've got the horizontal force by the adult, and I'm just going to call that F of the H, the horizontal force, by the adult. And then I've got this force right here, the string pulling up at an angle, and I'll call this the tension in the rope. And then I've got the force of gravity on the kid, and I could call that mg, but they want everything in terms of W, and that's the weight of the kid. So I'm going to call this W right there. So that's the first step, draw a decent free body diagram. Next step, draw your coordinate system. Okay? Now, let me move this T a little bit because it's kind of in the way. This angle's theta, so that means this angle here has to be theta. So that's theta right there. Be careful when you draw your free body diagram. So now I've got my angle. So now I've got to break everything into components so that they stay along the coordinates. Oh, I got to label my coordinate system. I'm going to call this my positive x, this my positive y direction. Now that I've got that, I'm going to take that t and I'm going to break it into x and y components. So I've got a component of the tension that goes up. I've got a component that goes this way. This is t times the cosine of theta. This is t times the sine of theta. Again, I should have drawn a t over here to begin with. You likey? So now what they want us to find is, they want us to first find the tension right there, don't they? Okay? Well, if I draw, if you follow the method I taught you, and I said it works in every problem, start with your sum of the forces. So if I say, okay, the sum of the forces in the x equals 0, I know they equal 0. Why? Because the object is in equilibrium. The guy's just pulling back the swing. So I've got t sine of theta minus the horizontal force equals 0. So I know that t sine of theta is equal to my horizontal force. In the y direction, they also equal 0 because he's not moving again. So start with your positive y. T cosine of theta equals w. So now I can easily solve for t here. I should have started with that. But I want to go through the steps I told you. Draw a free body diagram, set an x and y coordinate system, choose it wisely, break everything into components, write your equations. Either set them equal to ma or set them equal to equilibrium. So T is going to be equal to W divided by the cosine of theta. So there's our first answer right there. That's pretty cakey-esque. So now I need to find my horizontal force. The part B asks, what's the horizontal force exerted by the adult? Well, I just found T, and I know the horizontal force is T times the sine of theta. So I can substitute over here, W over the cosine of theta times the sine of theta equals f of h. So therefore, sine over cosine equals tangent of theta. So my horizontal force is W times the tangent of theta. Well, that's pretty neat. So now I have that. So I have my horizontal and I have my vertical. Alright? So then what happens? Well, now what happens is the last question. It says, find the tension in the rope as a swing passes through the lowest point. I wanted to focus on this for a couple of reasons. There's another question it asks, but I want to skip that part for now because I wanted to focus on the circular motion part. What's going to happen is this thing is going to go down this right here, and you got to figure out the tension at the bottom when it reaches the bottom of the swing. Okay, what's the tension right there? And so what happens is, let's draw a free body diagram at the bottom of the swing. At the bottom of the swing, you're going to have the tension of the rope pulling up, and we're going to have the weight of the kid, W, going down. And I drew T bigger than W because it's going in a circular path, so there has to be a centripetal force going upwards. Now, in this scenario right here, it's all right. In this scenario right here, I'm going to, when it's going in a circle, I don't really call it X or Y. I just say the sum of the forces causes the mass to accelerate. But since it's going in a circle, this acceleration is centripetal. So I'm going to call that a centripetal force. And so this is positive. You always make toward the center of the circle positive. So the net force going toward the center would be T minus W equals M times the centripetal acceleration, which is V squared over R. Right? Well, that doesn't help me very much. I know the tension is going to be equal to W plus mv squared over r. But they want the answer in terms of L and everything else. Well, I know right now that at the bottom of the circle, that radius becomes the length. But they want all their answers in terms of W and theta. Alright? Now, right now, if this was the test that I was giving you, in order to find V, I just realized I'm going to have to use conservation of energy. And I'm going to have to find the potential energy here and convert it to kinetic energy there to find my velocity. But that's beyond what we've studied so far. So all I want you to worry about now for your review is just, if you just understand this process I went through. You can set up the same coordinate system like we did before with Newton's laws. But instead of setting it equal to 0, you set it equal to ma because it's accelerating. And since it's accelerating, it's equal to v squared over r. You make your coordinate system so the center of the circle is positive, and then you just look at what are your forces. T minus W. Those are your centripetal forces. Notice I didn't put centripetal force on a free body diagram. That never goes up there. So we've got T minus W equals mv squared over r. And then I could solve for V. But I don't want to do that right now because if I do, I'm going to confuse you with stuff we haven't done yet this year. So I will finish this at a later date.